Hi, I'm Lucy, a Masters by Research student at Durham University, and this is some of my work on bubble rise in non-isothermal silicate melts. Eruptive volcanic activity is hugely diverse and fundamentally linked to the dynamics of bubbles within the plumbing system, more specifically the organisation and relative rise rates of gaseous bubbles in the magma. A lot of existing work on bubble rise has looked solely at isothermal settings, where melt viscosity and bubble size remain constant throughout. But the problem here is that we know there to be spatial and temporal changes to temperature within volcanic systems. So to improve on previous estimations, these non-isothermal conditions need to be factored in. To model this analytically, changes to viscosity and bubble radius are integrated into the Hadamard-Rosinski equation to determine a bubble position at any given point in time. Experimental data to validate this approach was collected by adapting an artistic bubble entrapment method, allowing bubble rise to be observed in a soda-lime silicate glass for a variety of different kiln programs. Comparing the final observed with rise heights to those predicted by the model, there appears to be a good correlation, especially for smaller bubbles. The model does begin to slightly overestimate rise for larger bubbles. However, this is still encouraging data and shows that an integrated form of the Hadamard-Rosinski equation can still be used to estimate bubble position through time in a silicate melt. This validated approach can now be extended to a wide range of applications. In artistic or industrial settings, it could be used to help control kiln-based glass manipulation processes. For a volcanic setting, it could be used to estimate the critical bubble size for a separated gas magma flow in either a cooling conduit or a conduit with substantial vertical temperature changes. Both applications would aid understanding of bubble rise and its role ultimately in defining the eruptive behaviour of a volcano.